Hey there, chemists. We're going to start our next unit on radical reactions. And when you hear the word radical, you might think of a mathematical expression like that, but that's not what we mean for organic chemistry. A chemistry radical means an unpaired electron on some atom. For example, here's a methane molecule. But let's get rid of one of those H's and instead put a single dot, meaning an unpaired electron. That's a radical that we're talking about. They're very reactive species, and they're hard to generate, and more so, they're hard to keep. So once you make one, it usually always reacts. What we're going to use them for is to do halogenation reactions. So a halogen, such as chlorine, elemental halogen, can react with just an alkane, such as cyclopentane. And under photochemical conditions, which we use the symbol H and nu, meaning Planck's constant times the frequency of light, you get a substitution product. So a haloalkane. And then there's a byproduct. In this case, you get HCl. So that H nu, it looks like a V, but it's the Greek letter nu, just means photochemical. So there's special light that's used for this. I want to use this as an example of our first synthetic reaction, and more so to show you the mechanism in which it occurs. Now, a mechanism is a series of steps that involve bonds breaking and bonds forming as we go from reactant to product. Now, the first part of this is called an initiation, and that's simply when the halogen molecule breaks apart and becomes two halogen radicals. Now, just like we use curved arrows to show how electrons delocalize in resonance contributors, and even a little bit of how they change in acid-base reactions, we use curved arrows here to show what bonds break and what bonds form. But unlike the traditional arrow that implies two electrons like that, we have radicals, which are only one electron, so we're going to use what's called a fishhook arrow. It looks kind of like a half-headed arrow. So what we have is this chlorine-chlorine bond broke. One electron went on one chlorine, and one went on the other. So I show that by drawing an arrow from the chlorine-chlorine bond to one chlorine atom, and then a second fishhook arrow from the same bond to the other chlorine atom. That's a complete arrow-pushing mechanism for just that one step. Now that's the hard part, generating these chlorine radicals. Well, once you make one, they're so reactive that if I have one floating around in my reaction mixture, there it is, and as soon as it sees an alkane, such as cyclopentane in this example, it will react with that alkane, and you'll generate an intermediate, in this case a cyclopentyl radical, and this is also where you generate that byproduct, the HCl molecule. So what bonds broke and what bonds formed, and how do we show curved arrows to explain those? Well, we broke a CH bond off of that carbon. There used to be two hydrogens on that carbon, and now there's only one. We formed an HCl bond, and that's it. So I got to use curved arrows to show that in these starting materials for that step. There's one electron from the chlorine and two in the CH bond, so I need three fishhook arrows to account for all three of those electrons, and here's how you draw it. I draw an arrow from the CH bond to the carbon where the electron ends up. I draw a second arrow from that same bond sort of halfway, meeting up with the chlorine. I draw a third arrow from the chlorine radical to that CH bond. Those three curved arrows show me all the electrons that are involved, and it communicates that I'm forming a bond between the H and the Cl, I'm breaking the bond between the C and the H, and I'm getting a new dot, a new radical on that cyclopentyl ring. That's propagation step 1. Propagation step 2 involves this new, very reactive cyclopentyl radical that we just made. We have an intermediate produced in an early step, consumed in a later step. Now that cyclopentyl radical sees another chlorine molecule, and this is where you generate your haloalkane. You get your chlorocyclopentane, you actually regenerate another chlorine radical. So we consumed a chlorine radical, and we regenerated a chlorine radical. That's not an intermediate, that's called a catalyst. A catalyst is consumed and then regenerated. An intermediate is the opposite. It's generated and then consumed in a later step. They both sort of cancel out of that net reaction, don't they? And you can see that we have our overall reaction right here if you sum those two steps. Anyway, what do the curved arrows look like? Well, we're breaking the Cl-Cl bond, and one of the electrons goes on the chlorine. The other chlorine radical, the other electron, teams up with this cyclopentyl radical, and that shows the forming of the bond between that carbon and that chlorine. Now I want you to box out those two steps because those are where all the chemistry comes from. That's where the bulk of the formation of this reaction gives us the product, because we have, as I said a moment ago, our reactants, cyclopentane and chlorine, making chlorocyclopentane and HCl, and we have catalytic chlorine radical and intermediate cyclopentyl radical. Now there is another part of this mechanism, we call it the termination steps, and it's just where any two radicals meet up and make a neutral thing. So there is another path that could involve a chlorine radical seeing a cyclopentyl radical, and yes, that is just a separate path under which you could get the same product. But think about what's going on if you did this in a laboratory and you have a flask filled with all of these chemicals. As soon as you generate that chlorine radical, it's going to find a neutral cyclopentane ring that's not yet as a radical. It's much less likely for the two radicals to find each other. It does happen, so we show it. What's also possible, so I'll say and, two chlorine radicals could see each other and actually regenerate a molecule of chlorine. That's another termination step. In fact, there's another one as well. We could have two cyclopentyl radicals team up, I'll just say times 2, to give you this larger dimer involving two cyclopentane rings fused together. So if you're doing this reaction and you fish that out, you have a reason why it happened. You have an explanation for this. Okay, so let's go back to those propagation steps, because that's where all the reactants and products really predominate in terms of what turns into what. And I want to use this as a way of looking at an energy diagram for a reaction so we can talk about going forward in this course. An energy diagram usually plots the change in enthalpy of a reaction as the reaction proceeds from reaction to progress. Now the change in enthalpy we're going to use is whatever energy is devoted to breaking a bond minus whatever energy is devoted to forming a bond. So broken minus formed. Remember, very fundamentally, every time you have a bond and you break it, you have to give that bond energy in order for it to break. So breaking bonds always absorbs energy, forming bonds always releases energy. Now we have a table of bond energies down below, so we can use this and look at what bonds form and what bonds break. Well, what happened in the first propagation step? We broke a CH bond. So we broke a CH bond and we formed an HCl bond. What about the second propagation step? The second one broke a Cl-Cl bond and we formed a carbon chlorine bond. So let's go down below and find what those energies look like. If I look for the breaking of a CH bond, I see 3 of them. They're not all created equal, but the one I think we're going to use is the secondary one, because that's a secondary carbon, meaning it's attached to 2 other carbons, so I'm absorbing 95. We are forming an HCl bond, 103, so I have 95 minus 103, and I get negative 8 kcal per mole. That's just for that first step. What about the second propagation step? The second propagation step broke a chlorine-chlorine bond, 58, and it formed a carbon-chlorine bond. And again, there's 3 types, but we're forming a secondary one, so we're releasing 80. So I have 50 minus 80. Sorry, 58 minus 80. Let's fix that. 58 minus 80, which is negative 22 kcal per mole. Now, why don't we bother calculating the delta H for the other steps, the initiation and the termination steps? Well, in terms of moles of molecules and intermediates that are undergoing this reaction, they are negligible in just how many of them actually occur. Again, it takes 1 molecule of chlorine to give me 1 chlorine radical, and that's sufficient to go and do this reaction in a chain reaction, essentially. As I generate 1, it can cycle back and be reused, because as soon as you generate one, it's a catalyst and it gets used over and over again. So I'm only going to look at those two energies, those two steps. And lastly, let's just plot this on an energy diagram as we go from some arbitrary place of our reactants. That's our cyclopentane ring and our chlorine. We go down 8 kcal per mole for step 1. So I'm going to draw another horizontal here. This is where we generate our intermediate, which is our cyclopentyl radical. And then we go down 22 more, so even farther down, to get our product. So this just shows what it looks like relatively from reactant to product. This is our intermediate, this middle part, as we go from reactants to products. Now, there's also a path under which this reaction took, and we're going to approximate that with a curve that looks something like this. And that shows two other things that we don't have structures for, but that's worth labeling. Those are called the transition states. Remember, these are the high energy activated complexes that exist in between the reactant and product of an individual step. You could label other things if you wanted to. If you remember from your past classes, there's an activation energy for each step. We don't have any kinetic information, so I don't really know how tall those crests are, but we can just draw them as something arbitrarily vertically up. We would need kinetic information as opposed to thermodynamic information. Okay, so that is what a radical halogenation reaction looks like. This is how you take an alkane and turn it into a haloalkane. Let's just do 1 or 2 practice problems on the back, because this points out that we can do things other than chlorination. We can do bromination reactions. Mono means what we've been looking at, just replacing one hydrogen with a halogen. So if I took propane and treated it with bromine and light, I could replace any one of these hydrogens with a bromine, and I would get that, 1 bromopropane. Unlike the cyclopentane example in the front, this molecule has multiple different types of hydrogens. We also have the possibility of 2 bromopropane, don't we? So we're looking at all possible products. And it can get even more complicated. If you look at B, this is just butane. But if you do the same reaction, bromination with light, well, I could have 1 bromobutane. I could also have 2 bromobutane. And once I draw that, I'm reminded of our previous unit. That's got an asymmetric carbon in it. So I could actually have 1 stereoisomer of 2 bromobutane, or I could have another stereoisomer of 2 bromobutane. So if your molecule is not completely symmetric in the beginning, you have the possibility of multiple products. But that's going to lead into our next lesson on how can we predict which product is major from these. The good news is you don't get all of them. You have in equal proportions. You have different selectivities for them. That's what's coming up next. Okay, that's how we take alkanes and turn them into haloalkanes using radical halogenation.